Hello everyone, my name is Mingshu Zhai. Today I'm excited to introduce our work, SmartMoE, efficiently training sparsely activated models through combining offline and online parallelizations. This work is conducted at Pac-Man Lab, Tsinghua University. Our team members include Jiaao, Zixuan, Zhang, Runqing, and our professor Jidong Zhai. In recent years, we have witnessed the rise of powerful AI applications such as ChatGPT and Stable Diffusion. Both of them are based on pre-trained models. Sizes of pre-trained models grow every year. As people have observed, larger models tend to yield higher accuracy in downstream tasks. For instance, 4 years ago, GPT-1 only had about 300 million parameters, but in last year, Google released a model with more than 500 billion parameters. Currently, the scale of pre-trained models is constrained by computation resources. Therefore, it's important to answer the question, how to scale up to extremely large models at an acceptable cost. A promising solution is mixture of experts, which enables scaling model size without adding computation. For traditional dense models, increasing model size means more computation. However, scaling with MoE is more efficient. The original small model is considered as an expert subnetwork, and the large model consists of many such experts. During the training process, a gating network activates only a subset of the experts, preventing an increase in computation. As a result, by employing MoE, we can scale model size together with throughputs, which means we can get higher accuracy within the same training time. So we believe that MoE represents the direction of large-scale models. As model size grows, training efficiencies becomes increasingly important. Many strategies have been proposed to enable distributed training, such as data parallelism, tensor parallelism, and pipeline parallelism. However, to achieve optimal performance, it's necessary to combine these strategies, which we refer as hybrid parallelism. Hybrid parallelism requires system experts to fine-tune for the best configuration. It is very challenging for machine learning users. So to make it easy to use, automatic parallelization systems have been proposed, which can find the optimal configuration automatically. As MoE becomes promising, expert parallelism has been proposed and optimized. Similarly, some work has explored hybrid parallelism for MoE models. But for auto-parallelization, due to MoE imbalance and dynamic properties, existing works fail to handle MoE. This is where our work, SmartMoE, comes in. It is a dedicated automatic parallelization system designed for MoE models. To understand the limitation of existing works, let's first delve into two key properties of MoE, imbalance and dynamic workload. In the MoE training, each node processes different input data. The gating network independently assigns experts to each token, which may be located remotely. This introduces an audio communication to rearrange the data. This can lead to overloaded experts and finally resulting in an imbalanced workload. It could hurt training performance because there are some low GPU utilization. In addition, MoE models has a dynamic property. The activated expert changes from one iteration to another. So it's very challenging to predict the overloaded expert. Actually, the dynamic workload makes the experts unpredictable. Given these two properties, an ideal system should satisfy two requirements. First, to deal with imbalanced property, the chosen execution plan should be workload-aware, which means it should know the workload situation of each expert. Second, to deal with dynamic property, the chosen execution plan should be ever-changing to fit the current workload. We think that existing approaches cannot meet these requirements because there are some limitations in their workflow design. For dense models, they search for efficient execution plans before training starts. During runtime, only pipeline scheduling are performed. This method has two limitations. First, the search is not workload aware. And second, the execution plan is static. For MoE models, moving the search process to online stage does not solve this problem because the search efficiency is not acceptable. Both online search and switch are slow and could incur significant overhead. In summary, existing approaches fail to deal with MoE models. So therefore, we propose SmartMoE. First, it provides an enlarged space for hybrid parallelisms, which support workload-aware search. Second, it has a unique two-stage automatic parallelization approach, which can handle dynamic workload efficiently. Finally, it is a complete high-performance training system, achieving leading MoE training performance. Our key idea is to breaking the process of search into two stages. In the offline stage, we construct a comprehensive search space, and we can obtain a candidate pool containing a small number of promising execution plans. So in the online stage, we only select plans from the pool, which improving efficiency through pruning. SmartMoE supports hybrid parallelism for MoE models comprehensively. First, it supports any combination of the classic parallel strategies, which previous works have not completed. For example, Megatron was designed only for dense models, so it does not support expert parallelism. FasterMoE is optimizing expert parallelism, so it does not consider other strategies. Bagua and DeepSpeed MoE began exploring hybrid parallelism, but still fell short. In contrast, our system offers complete support. Furthermore, we discovered a new strategy for MoE called expert placement. Using an example of 4 experts placed on 2 devices, if experts 0 and 1 are overloaded, the device 0 will be heavily overloaded. Although we cannot change the workload of the experts, we can achieve balance between devices by altering their placement. We call these different configurations expert placement plans. By using different placement plans, we can address various workloads. To enable two-stage parallelization, the key is to define the pool. We define the pool as a collection of execution plans that only differ in expert placement. So, in this definition, the offline stage accomplishes the combination of the classic parallel strategies, leaving placement plans for the online stage. This design retains sufficient flexibility for online adjustments without introducing much overhead. For more details, please refer to our paper. Finally, we showcase the test results of SmartMoE. Our experiments considered various scenarios. We used 3 clusters with different types of GPUs, network bandwidth, and scales. For models, we selected GPT-MoE and SwingMoE. We compared our system with 4 strong baselines, including DeepSpeed MoE, FasterMoE, Two-Tail, and APA. It should notice that we did not directly compare our system with APA. In end-to-end training, we achieved excellent results across different model structures and clusters, with near 2 times speedup. This success is due to our two-stage parallelization. In ablation study, we validated the effectiveness of the offline stage. Our system can find better strategies than previous works because we have a larger space of parallelism, and we use a workload-aware performance model to select the execution plan. And in the online stage, we obtained further speed up. We applied dynamic placement strategies for different layers at different iterations, achieving at most 1.4 times speed up. Moreover, we find that the frequency of dynamic search is crucial to performance. We tried different frequencies of adjusting from low to high. Both too low or too high frequencies resulted in suboptimal performance, so careful adjustments are needed to achieve optimal performance. In summary, two things are important. First, hybrid and workload-aware strategies are necessary. Second, the search algorithm should be split into two stages. In our proposed SmartMoE, it has a comprehensive search space to address dynamic workload. It also has an efficient two-stage search algorithm. Finally, it successfully achieves state-of-the-art training performance. Our work is open source on GitHub. You can scan the code to find it. Thank you for your listening.